So welcome everyone to the joint colloquium between INCEMAD, the Research Center of the SIC, and 3 universities of Madrid, Universidad Autónoma, where we are, Universidad Complutense, and Universidad Carlos III de Madrid. I'm happy to see we have representatives from each of the institutions, which is nice. Yes, Complutense is also here. So today's speaker is Manuel Castro from Universidad de Málaga. Manuel is an expert in numerical analysis of partial differential equations. He trained in Paris, Pierre Marie Curie, then Paris 6.
Paris 6, at my time.
And he's a full professor in University of Malaga since 2020. He has many distinctions, among which Juan Luis has already reminded us that he was the president of SEMA for a stint, which we are all very thankful. And he's a very distinguished researcher, which he will demonstrate in his talk. We also have to be thankful that he's also willing to take on administrative duties, and he's currently in the panel of the agency, which I'm guessing takes a significant time. So thanking the research is easy. This comes in publications and students and things, and thanking the other side, of the less glamorous side of the academic life, I think we also have to thank him for. His talk today is about path-conservative numerical method and well-balanced schemes. And thank you for being with us today.
So, thank you, David, and thank you also for the organizers of the colloquium for the invitation. So, for me, it's a pleasure. Let me say that for me, it's the first time that I'm in the Autónoma. So, I have been visiting the Complutense, Politecnica, but for me, the first time here. So, I also, thanks to be here, and for me, it's an honor to participate in this colloquium. So, this talk is more like a review of things that we are doing in the last 20 years about the numerical approximation of hyperbolic PDEs. So there is not much novelty in the things that I'm going to talk. More the result, I will say, are classical results, classical in the sense that have some years, okay, of since they have been published. And in order to try to be clear in my exposition, I will only consider 1D problems in order to fix, the main ideas and the main difficulties. Most of the things that I'm going to show could be extended to multi-D. There are some technical details in certain situations. Of course, the implementation is much harder than when you do numerics. But from the theoretical point of view, the numerical point of view of the analysis, then a lot of things could be more or less extended without too much difficulty. I'm a member of a Dania group. So the Dania group was created by Professor Antonio Valle, that is also well-known among the people that belong to SEMA, but also in the PDEs and numerical analysis community. And Dania means ecuaciones diferenciales, análisis numérico y aplicaciones. So, as you believe, so I'm going to present, PDEs of the kind of hyperbolic PDEs, non-conservative hyperbolic PDEs, and then the numerics, and then some application to real problems, because the model that we develop, I use in many practical applications, like in center of tsunami early warning centers, and they use the model that we provide in order to calibrate the impact or hypothetical or a real tsunami that is occurring in any place in the world. So as I said to you, this is our toy problem. So we consider a Cauchy problem one-dimensional. So W here is the set of unknown that lives in an open convex set. Then in this talk we suppose that F, that is the physical flux, is smooth function. B is a matrix that defines the non-conservative fluid is also smooth, and then we have also a source term that depends on the unknown but also on the space value. So typically, for example, if you think in shallow water system, so the source then will take into account the gravity effects, so the top of asymmetry, the derivative of this function appears. Things could be even more complex and could be extended, for example, if we consider non-smooth flash functions. So, for example, you could things if you have different materials, and then you could connect these, and then most of the things I'm going to say could be extended without too much difficulty. And here, okay, for me the tricky things are this non-conservative product and the source term. The source term could be even non-smooth. So, for example, a typical, I will show an example. So, a typical thing is you could have some S of W that is algebraic, but then multiplied by something that is the derivative of a heaviside, so a delta function like that. Okay, and I want also to do numerics in that framework. So we consider an initial condition, and in the hyperbolic world you must be also careful if you are treating in bounded domain with the boundary condition. So you must properly deal with the incoming and outcoming characteristics in order to impose coherent and proper initial condition in order to deal with boundary condition in order to deal with this system. So even if in the application system that are written in the previous way, for doing the analysis, I prefer to write in a more compact way, like a quasi-linear in the quasi-linear form. So I rewrite the system by increasing the unknowns by adding an artificial unknown that is the space variable, and then I could write the system like that. And here, what is, here you cannot write this, as a conservative system. So this is not the derivative of a flux function, okay, in our framework. And then I suppose that I'm in a simple case where our system is strictly hyperbolic, so we could diagonalize the matrix. Difficult problems appear when you have, for example, resonance. So in that case, also the analysis of that problem is also tricky. You cannot, for example, in situation where you have resonance, you cannot, even if you play with entropy conditions, things like, you cannot ensure, even for a Riemann problem, unicity. For example, you could have several families of solutions that satisfy the entropy condition. This is, for example, a case in shallow water with the singular source term, also with the Euler equation in 1D channel. So there are tricky things with this simple problem. Then, in the framework of hyperbolic PDEs, a typical initial problem is, the Riemann problem. So the initial condition is given by two constant states that are not necessarily continuous. So you have a jump here. And then, okay, I want to ensure, as in the case of a standard conservative system, that I'm able to solve this Riemann problem. And for that, for example, we could assume that we are in this framework. So either the characteristic fields are degenerate, linear degenerate, or genuine non-linear. So in this setting, if the jump is not too big, I could solve the problem using the simple waves like shock, rarefaction, and contact waves. As in the case of conservative system. So everything could be extended in this framework without too much difficulty. And also, from the practical point of view, I'm also interested in, in approximating a very efficient way and precise way the steady state of the system. So solutions that satisfy this, let's say in 1D, this ODE, okay, ODE system. So in many applications, what we want to have is to develop numerical schemes that exactly preserve, up to massive precision, the steady state characterized by this system. And we want to do that because we want to also simulate small perturbation around that equilibrium. And from the numerical analysis, the schemes that somehow are able to preserve the structure of steady state are called well-balanced schemes. Okay, so part of the talk is developed to describe the, how we could construct a numerical scheme that are exactly up to machine precision for certain steady state. All of them are representative family of them. This is part of also something that is also interesting in our community, that is what we call a structure preserving scheme. So somehow we have a structure that has, the continuous problem has solution with a given structure, and we want to preserve this up to the numerical point of view. Okay. So this is also something relevant in this framework. So first problem that we deal when you try to do some numerics and approximation of this system. So the first thing that you need to characterize are what are the weak solutions for that problem. Because in a hyperbolic system, even if you start with a smooth solution, for in a finite time you have discontinuities. So what is the meaning of this? Okay, you have this non-conservative product. What is the meaning of this? Because this is the derivative of a discontinuity, let's say high size function times discontinuity. So you cannot establish or work with the standard distributional framework. You need to enlarge and to play with another setting. And the setting that we aim to play with is the setting developed by Dalmason and Flockmore. So for giving a sense to a weak solution, we need to add an extra information to the system that is a family of facts. So let's say that when, from the mathematical point of view, when you write a system like that, you need also to prescribe something more, because if not, you cannot characterize what are the weak solutions for that system. And the extra condition that you need to give is this choice that from the mathematical point of view could be any, let's say, smooth family of parts that connects discontinuity in the space of states. Of course, from the physical point of view, it's not the same. But from the mathematical point of view, playing with the regularity of this function, you could give a sense. Other thing is that what you recover is what you expect from the physical point of view. Okay. So, roughly speaking, what is a weak solution for that system? So where it is smooth is a classical solution. When you have discontinuities, the weak solution should satisfy this generalized ranking Monnier condition. So suppose that A is the Jacobian of a flux function. So integrating this is nothing more than the jump on the flux is equal to the jump of the state multiplied by the velocity of the propagation of the shock. So this is the natural extension of the standard ranking Monnier condition here. Okay? Of course, as in the conservative framework, you need to play also with entropy. So in order to select physical admissible solution, you need to add to this system, an entropy pair with a convex entropy, and with this you are able to pick up, from the weak solution those solution that satisfies the generalized ranking Monnier condition, those that has a meaning from the let's say physical point of view. Okay, as in the conservative framework. So let's say from the mathematical point of view, in order to define properly, weak solution, you need to prescribe the system, what is your choice of path, and an entropy pair. And with this, you have the same. You could extend, all the things that we know in the conservative framework to this framework. Okay, it's what we need.
Manuel, can I ask you about the entropy condition?
Yes.
Because once you have the non-conservative structure, what is the entropy flux?
So
what does the entropy flux look like?
Well, let's say, if you consider, for example, let's say, you have this kind of systems. So this system appear naturally, for example, when you have multi-phase fluid flow. So typically fluids connected by a condition, an interface for pressure, multi-layer saltwater system. So you are able to combine properly the mass and momentum equation, and at the end you obtain an entropy similar to those that obtain in a conservative framework. So for example, in the case of shallow water system or Euler, so you play in the same way, so you have several multi-phase, but you do the same play, and then you obtain something that is similar to an energy thing. Okay?
But the entropy flux then is
more
complicated. It's more complicated.
Yes, you need to add more terms. You need to add more terms. For example, you have a source term, then the source terms appears also. The term SWX also appear in the in the entropy flux. So it's not trivial to obtain an entropy pair, but could be done. Okay, could be done. At least for the system we play with. So let's say multi-phase Euler system, multi-layer saltwater system, some kind of extension of Riemann model. So most of the problems related to fluid dynamics in this setting. But you could do, okay? More complicated, but you could do.
But you could do what you can do. Sometimes you cannot do.
So let's say if you take, for example, there is a typical example that engineers like quite a lot, that is shallow water with sediment transport. It is the grass model. So you have shallow water and then an empirical equation for the transport of sediment. So it's, let's say, a 3x3 system. So in that case, if you play with this system has not an entropy associated to that. So from the mathematical point of view, it's a system that I don't like. Okay, because I'm not able to do a mathematical, my mathematical framework don't give me the tools necessary to understand what are the solutions. So for example, one thing that we have done for that system is, okay, let's try to derive using the same principle, as in the multi-phase flow, but assuming some assumptions, provide a new model that is a modification of the grass model in order that to have an entropy associated to that. So one part of our work in our group is not only do numerics, but provide new models that at least from the mathematical point of view has, an energy, an entropy associated to that, so that from the mathematical point of view, we have something to deal properly, okay? But if you take, system coming from the engineering approximation of problem, then you cannot ensure that this system has an entropy associated to that. Okay, so what is the solution, the admissible solution for that? Okay, and this is something that we also work on. So how we choose these families of paths? I say, from the mathematical point of view, any possible family of smooth function connecting this continuum could work, but from the physical point of view, there is a connection between these, the family of paths and viscous properties. And this is, in fact, pointed by Lefloc. So typically, okay, think that in your problem, your non-conservative system comes from, the parabolic regularization of, that system. So you have a epsilon, then you have a viscous term, and then you are trying to characterize what are the viscous profiles. Okay, viscous profile are nothing more than traveling wave that could be written in that form with these standard, boundary conditions. Then V, the solution of this equation, and if you integrate and use your boundary conditions, you have this. Okay, you have this. But this is nothing more than a reparametrization of this. So what are the relation between the paths and viscous profiles? So it is clear, no? So path should be reparametrization of the viscous profiles. So what are the good paths? So let's say you take your system. Let's say you start from Navier-Stokes. You do some simplification because you are thinking, in a multi-phase flow, etc. You do the simplification. Then you need to properly characterize the viscous profiles, and with that, you are able to characterize what are the good family of paths. Okay? But this is a very, very difficult problem. Only in toy problems we are able to do it. Okay? But it's really difficult. So what happens if you are not able to compute this? Okay? Okay, from the mathematical point of view, what you are doing is changing, the notion of weak solution. So, for example, the velocity of propagation of shocks. But if you are not able to do this, let's say, okay, take a simple family, so segment. This was done to me, okay, long time ago. And then, okay, you could try to characterize what are or try to measure the error that you introduce by replacing this good path by a simple family, for example, segment. So this is something that we have done here. So for example, if you take segment that is very simple, of course, you are introducing an error, okay, you're introducing an error that is a third order in terms of what? Of the jump of the discontinuities, okay? So, you could think, okay, but then you have changed the notion of weak solutions. Yes, but you could also think that this is somehow, if you are modeling a problem, okay, you are modeling a problem, you do some assumptions, and then this is part. If you are not able to characterize the good part, and you take another simple part, this is an error in the model, because what I said to you is, okay, for me, in order to fix the model, you need to fix the equation, but also the path. So what you are saying is, okay, my model is, the PDE plus a simplification of paths. Of course, there are problems where you cannot do that, okay, because you are saying, okay, I want to really capture properly what are the true shocks associated to the viscous profile coming from that, okay? But then the effort is, okay, you need to be able to characterize this. Of course, you could improve and try to approximate this somehow, okay, if you're not able to compute. And there are also works in the literature trying to do that, okay? But this is also a difficult problem. And this is, for me, this part of modeling, okay? It's not numerics. So it's how to close properly from the mathematical point of view the system with the path and the entropy, okay? Now, if we have this, now we start the numerical approximation. And we need to start the numerical approximation in this setting, okay, in this setting. So, okay, what I'm going to show is, in the framework of 5 volumes, but everything could be extended in DG or 5 difference. You must be careful, of course. But everything that I'm going to show is in the 5-volume approximation. So you have your cell that we suppose that is, constant size, and then we try to evolve, the cell average. That is the standard quantity that we want to evolve in this kind of problems. And okay, something that is, made at home is the notion of path conservative. So path conservative maybe is our main contribution in the field of numerical approximation of hyperbolic speeds. And this notion was introduced by Carlos Paez in a Sinum paper 20 years ago. So let's say in the simple case of low order, so 3 points scheme, a path conservative scheme is a scheme that, okay, time is continuous, I only think in discretized space, okay? So a path conservative scheme is a scheme that could be written in this way, where this D minus and D plus what we call fluctuation, should satisfy these two properties. So the first property is related with this natural or standard consistency for smooth equation or smooth solutions, and this property is the consistency with respect to the choice of paths. So, okay, this is, so the path conservative scheme is a way of splitting this mass, because remember that we have a non-conservative product, so the non-conservative product should be understood at a Borel measure, so we have regular part, and then in the singular part we have delta mass there, and then we need to split, the mass associated to the discontinuity in this way. So this is the consistency of the numerical scheme with respect to the choice of paths. Even more, suppose that A is a Jacobian of a given flat function, okay? So a path conservative scheme is a standard conservative scheme if your system is conservative. So for example, if your system have subsystems of equations that are conservative, automatically the path conservative framework ensures you that your method is conservative for those subsystems of PDEs. Okay, this is also a very important property, and this is due to that property. Okay, so this is a general framework, and using this framework we have developed and extended most of the well-known Riemann solvers to that framework. So Godunov, simple Riemann solvers, entropy preserving. So we have extended the framework of Tadmor to this setting in order to control and to construct entropy preserving scheme. Okay, let's say a lot of different Riemann solver with different properties has been extended using this setting. But the main question is, okay, use whatever path conservative scheme. Are you able to prove the convergence to the weak solution? So we are able to prove in this setting a last Wendorf theorem for this kind of system. And this is what we could prove, okay? And good and bad news, okay? Good and bad news. So, okay, suppose that we are in the same framework that in a conservative system. So we have, a sequence of numerical approximations. Those should satisfy that the amplitude of the total variation should be bounded uniform in time, as in the conservative setting. Then what happened? So, if any sequence of this converging almost everywhere, that is the standard conversion, notion of conversion that we use in this setting, to a function, what happened? Is this function a solution of this system? And the answer is, with this notion of convergence, no. What you introduce is a bounded measure. So W, okay, is the solution of this perturbed PD, okay? And you cannot reduce this error by reducing the space discrimination. You can't. This measure is concentrated at discontinuities. So that means that your method is convergent, but to another solution, okay? To another solution. Okay, so this is the bad news. So if you take any path conservative method without care about controlling the entropy dissipation or controlling the kinetic relations, you cannot ensure that converge to the homogeneous product. You cannot. Okay, but okay, you could try to enforce.
Question. The second term has subscript phi. What is this thing?
So that means that this.
No, the second. No, sir.
Okay.
What is this?
Okay, this is, okay, when you define the non-conservative product,
Yeah.
depends on the definition of this path. So that means that, okay, when you have the PDE and you have the family of paths,
Yeah.
you know, we prefer to represent, okay, the weak solution with respect to this phi, because the weak solution depends on this choice of path, okay? So, when you have a non-conservative system, if you say nothing, you cannot say, well, okay, what are the weak solutions? For defining the weak solution, I need to prescribe a family of paths. So this is, okay, the interpretation of this non-conservative product, taking into account that I have chosen this family of paths. So in fact, if I change the family of paths, the weak solution will be different. But this is
Because
something.
if you go to scheme, you see that the phi is in the definition.
In the scheme, yes. So is in the definition of the weak solution, but also in the scheme, in the numerical
Where?
scheme, are here.
Ah.
Because this D depends implicitly on phi here, okay? So in fact, you know, from the very beginning, we always know this D sub phi, but then, you know, the notation is terrible, so we decided, okay, let's say, in this framework, you must know from the very beginning that everything depends on your path.
On the family of paths.
On the family of
How
paths.
many are there?
Infinitely many.
Then come to
But-
cover.
But then, you know, there are, as I said to you before, there is a natural way of defining, of choosing, you know, coming from physics, what should be this family of paths? Should be reparametrizations of viscous probability. Of course, this is a good definition, so that don't depends on the reparametrization, okay? So if you take a path and then it's the same, let's say, curve, but you reparametrize in a different way, you obtain, of course, the same weak solution. Okay, this is a yes.
But this depends on the velocity of the traveling wave. So at the end of the day, this is the one that you pick. And when you are applying this to a real physical problem, which one do you choose?
I don't know. So the question. So what I said here. So So if I'm able to characterize all viscous profiles for a system, then I'm able to construct a numerical scheme with this family of paths, okay? But if not, I say, okay, I take an approximation of this, for example, segment paths, to meet definition of a non-conservative product. But then we must know that it's our choice, okay? And we are trying to analyzing what are the errors that we introduce. Because for me, this is what I say, it's like an error that I introduce in the modeling, because for me, phi is a mathematical tool to defining the weak solution, but it's connected with the true physical solution that the viscous profile. If I'm not able to compute properly the viscous profile, I choose something that from the mathematical point of view has a sense to define the concept of weak solution. But I'm introducing an error. Okay, so for me this is an error. What, you know, from my side, this is an error of modeling, because I have the PDE together with, in order to close the problem to the family of paths. So what I have done is an assumption of the simplification of the path. So for me it's like, okay, a simplification of the true thing that I know from physics. So in fact, this family of paths in many problems depends on how pressure is computed at a given interface. So for me, it's okay, pressure at a given discontinuous interface, I'm going to compute in that way. And for me, it's like a closure way of defining pressure in a discontinuous interface. So this is what I'm saying, okay, for me, it's like modeling. You could say, okay, no, it's not modeling, it's a simplification of your mathematical problem. Okay, it's a simplification of your mathematical problem. And then you introduce an error and it's introduced and analyzed here. Okay? Now, but then, okay, I'm here, okay? So I could prove the conversion to the true system in this framework. So only with where the numerical solution converges in the uniform set of graphs. This is a notion that is established in the paper of Dalmas or Lefloc. So this is a very strong notion of convergence. Okay, it's more stronger than the religion. Okay, so the one question is, and there are numerical schemes that converge in that sense, and the answer is yes. They are difficult to construct, but there are some. So, for example, if you play with, green method or front tracking, they are viscosity-free method, and then you are able to capture properly this. So, or if not, for example, you need to control the what we call the equivalent equation of your approximation, or try to control the entropy production, or use kinetic relations. So it's like, in conservative system, when you have non-classical shocks, you need to add more information there, and then in that case, we are able to construct numerical method that converge properly to the notion of weak solution. For example, in that series of papers, we have proposed a numerical scheme that is like a local front tracking idea, and we are able to prove that this scheme converges properly in the sense of uniform in the sense of graph, and we have convergence. And we have papers with Mishra and with Lefloc, where we are try to control the entropy productions and try to produce numerical method that somehow try to minimize this measure error associated at discontinuities. But there are problems.
It is very interesting what you say, that you can use viscosity-free methods like green.
Yes. But for that, green method need to know the solution of the Riemann problem. Okay? But then, for example, here, in this paper, we could combine approximate Riemann solvers. So, it's a simplification of the solution of the complete Riemann problem, and a local front tracking. And for isolated shocks, we are able to prove that everything works. So it's a simplification. We don't need to know the exact solution of the Riemann problem. That is also a difficult task. Okay, this is also a difficult task. So, but for example, in this framework, paper with Mishra and Fihon, we are able to establish entropy preserving method. So you have a non-conservative system, you have an entropy, and your method exactly preserves the entropy. And then, as dissipation mechanism, you use the one coming from the physics, so associated to the viscous profile. So in that case, what you are able to minimize is this. Okay, you are able to minimize this. So if you are able to properly characterize the viscous profile, then the method automatically converges. But if not, this thing still exists, but it's very small. It's very small. Okay. It's a tricky problem. Of course, there are situations where it's not so dramatic. So, for example, if you don't have this nasty non-conservative product, so in the first case you have a source term, even if it's singular, and a physical flux. In that case, we are able to prove convergence. So this is for balance loss. And then also, if you have no conservative product but associated to linear degenerate field, like for example in the binunciator problem, so you have two-phase fluid with discontinuity in the interfacing pressure associated to a linear degenerate field. So in that case, you are able to produce numerical method that converges to the true solution, to the weak solution. So there are problems where the structure is simple and you could do something more. Okay. Okay, this is about the last Wendroff theorem. But what about well balancing? So well balancing is, the idea of preserving, a steady state. So here, what I'm showing here is the following. In red, this is a fancy bathymetry. So I have a fluid in a channel, 1D, shallow water, and zero velocity. So water is at rest. So the exact solution is, okay, there is no motion of the water, the free surface should be flat. This is the true solution. If you take any consistent numerical scheme, don't care about preserving the steady state, that in that case is very simple. It's constant free surface and zero velocity. This is what you obtain. So the water is automatically flowing, okay? And then your free surface is smooth. Of course, this error could be decreased by refining the grid. But for example, thinking of tsunami waves, maybe you need to take a small delta X to propagate a tsunami in the whole ocean. You want to preserve at least certain family of steady state in order to not to use so fine grids, okay?
Ese Vázquez Caillé es el gallego.
That's it. So this is the set property, okay? Established there. This is a very particular situation, and then everything could be extended and done in a more general way. Okay, what is the relation of well balancing and path conservative methods? So there are many ways of constructing, well balanced schemes. So schemes that preserve exactly all of a family of steady state. But what about well balancing in the path conservative? So the only thing that you need is your path should be reparametrization of pieces of steady states. So in that case, automatically you obtain the well-balanced property. So this is for free. So the well-balanced property in path conservative method is for free. The only thing that you need to provide is a good choice of paths. So, and in this case it's more simple because you are able to characterize in a simple way not all the path connecting discontinuities. No, it's only related to steady states. And those are
never used monotonicity of the gamma. Nothing.
We don't
No
need
structure on the geometry of gamma.
no, nothing here.
Oh, boundedness.
Yes, of course. Yes, of course. So, this is one of the reasons why path conservative methods are so popular in our community, because you obtain that property for free. Of course, you need to work with this. Okay?
The parametrization should be smooth, something.
Should be a smooth, so the path should be something smooth in the space of state. Even if you have a discontinuous steady state, path should be smooth. It's a smooth function in the steady state, okay? Okay. How much time I have?
15 minutes?
Okay. So, next thing. So I have, last Wendell theorem, okay, or at least what we could prove. Well balancing is for free, at least in low order method, not on high order method. High order method is not for free, but could be done. So next thing, what about entropy stability? What about entropy stability? Because in the last Wendell theorem, you only prove that your solution converges to a weak solution, but then you need to pick up those using entropy. So your numerical method is able to, so you are able to construct numerical method in this framework that preserve entropy. Of course, if you do code-node method, of course, yes. But something that we have thought is the following. Give me any numerical method, even for the conservative part. So Wt, that derivative of x of the flux function. Then you have a non-conservative product, and then you have a source node. I'm able to construct a path conservative method that have all the good properties that I expect, that is entropy, stability, for example, preservation of positivity of density, pressure. I'm able to do that, starting for a very rough numerical method, something that I know. And the answer is yes, in many situations we could do. So a simple thing that we could do is the following. Take any path conservative method that you have constructed, and you want to enforce the entropy stability. Then you could play by introducing some artificial viscosity. You are introducing artificial viscosity, so that means that you are modifying the viscous profile because you have your numerical method, you are introducing regularization, so you are introducing an error in your path, okay?
But you lose the jumps.
No. You still have jumps, okay? You still have jumps, but you know, what you want is that at the end you want to at the discrete level you want to recover the entropy inequality, and that gives you, you know, the stability condition for your numerical method. It's a nonlinear stability condition, more general than the standard. So, and there is a natural way of defining this parameter. So it's not tuning. It's, you know, somehow it's optimal. So what you do is, you know, it's a very technical work here, but you try to control the entropy production of the original system by this parameter. Okay, so I don't enter in too much detail because it's quite technical, but there are optimal ways of introducing a small amount of numerical viscosity in order to recover the stability condition, the entropy stability condition. And this is a nice way of doing. Of course, it's not the only one, okay? It's not the only one. It's also, we are able to prove that everything is well defined. This is a very new result, okay? This is a very new result. Also, we are also able to prove that the new state still belongs to the open set. So that with this result, we are able to prove if we start with positive density is still positive in the next step, pressure is still positive in the next step, satisfying this relation, okay? This is also a tricky.
So what is the condition of the open complex set? No condition.
So okay, you in that case you have no conditions. No conditions. Okay, and how we could do this or try to extend this to high order? In the fine volume framework, you know, it's more or less the same thing. So we consider a reconstruction operator and a first order part conservative method. And then, you know, here you use whatever reconstruction operator you want. Should be shock detecting, of course. And with this, the structure of the numerical method is that. Okay, you could think, but why the numerical method have this structure? Because in a conservative system, you don't have this, okay? You only have the difference of fluxes at the intercept. You don't have this. But think of, you know, the definition of, you know, this non-conservative product. The non-conservative product is, you know, could be understood at a border measure, okay? So inside the cell, everything is regular. So you have the contribution inside the cell. And then at the intercell, you have jumps. And then you use the first order part conservative system in order to split this hidden masses. So this is nothing more than the discretization of a model measure in the setting of 5 volume scheme. It's nothing more than that. Okay? It's the discrete way of thinking of a discretization of a model measure in that frame. And this gives you the natural way of discretizing or going to high order this system. Okay, and what about well balancing? So we are able to prove that if your reconstruction operator, if you start with you know, a given cell of sequences of state that are cell average of steady state, what we need is that reconstruction polynomial or operator, not polynomial but operator, still belongs to this steady state. But typically, this usual reconstruction operator are polynomial, and your steady state could be any. So you are able to present because this is what I need, because this is the theorem that I have. Okay, the theorem says that if your first order part conservative scheme is well balanced and the reconstruction operator is well balanced in the sense that is preserved steady state, then I have a theorem saying that the high order scheme is well balanced. But this is doable? And the answer is yes, it's doable. So what we do is the following. So first, in the first stage where I have a cell average, and then I need to compute, and this is a difficult problem, to compute a local steady state that have the same cell average as the one that I have at a given time. Then I extend the steady state in my stencil, and then compute the fluctuation. And then I reconstruct the fluctuation using a standard reconstruction operator that is typically polynomial. So what is my reconstruction operator? Is the steady state in the cell plus the fluctuation that I recover doing, the standard polynomial reconstruction. This is high order, conservative, and have the good properties, and it is well balanced. But 5 is difficult. Okay? 5 is difficult. But we could do in many problems. Okay? We could do in many problems. And I will show you some examples. So, and now, I'm going.
You have to have lots of stationary solutions to be able to start.
Yes, so what you have is a family of steady state, and locally, so typically, thinking 1D problem, okay? So the steady states are nothing more than, the general is a, let's say, multiparametric solution of an ODE system, okay? Depending on the initial condition, okay? You fix this by the cell average. So fixing the cell average allows you to pick one of them. If not, you try to, for example, do some control approximation or done some approximation in order to pick up for the whole family the one that is close to your cell average. Okay? And this is what I say is difficult because I need to fulfill this. So, and this is not an easy problem. Okay? But in many situations could be done.
Doesn't look very physical, right?
Sorry?
Doesn't look very physical.
Doesn't look very physical? No, yes. Suppose that you start in a steady state. I will show you an example, and I convince you. I'm going to convince you in a minute. Okay, let us consider Burger's equation with this fancy source term, and this. Okay, I have the derivative of h, and h is a discontinuous function. Okay, so what are the steady states? The steady states are nothing more than pieces of exponential with different rate, because I have here a jump of h. Okay, so this is a steady state. So in 0, where h has a discontinuity, so you have a piece of exponential, a jump, and a piece of exponential. So this is the exact solution, and this is what we obtain with a path conservative method that is well balanced, so preserve steady state, first, second, third order. At any order, I obtain, it is hard. The error is 10 minus 15, so 0 error. Because here, I'm able to characterize all of the steady state, so I'm able to exactly preserve all of the steady state. So my numerical method is able to preserve, to integrate properly this kind of solutions. Okay, this kind of solution. Okay, what happens if you play with the same problem without taking into account, the good choice of paths? So a naive approximation of the source term. You converge. So here is first, second, third order. Okay, first order is here, then second and third order. Match. You have convergence, but to a wrong solution. This is what happens if you change the path. Okay. So here, approximating naively the source term means that you have changed the notion of weak solution associated to this discontinuity at the source term. So if you want to exactly preserve this, you need to have an exactly well-balanced method, because it's not, okay, here any method do the job, but here you need to connect properly this jump.
Yeah.
Okay.
So these are not entropy conditions, solutions.
Could be entropy solutions, but could be entropy solution, because in this solution, in fact, energy is constant. There are not, let's say, there are constant weights associated with this continuity. Okay. And this is what happens if you use another regularization. So depending on the regularization you pick up, so the approximation of the source term, you convert to different products. Okay. This is the nasty thing when you have this kind of problems. And now I try to convince you why this is physics. Okay. So I start with a perturbation, and I have a well-balanced method. So what is nice in a well-balanced method is, okay, the well-balanced method is able to localize the perturbation. Here, nothing changed, because the propagation move, fade in time. So only affect to this part, but this part is. So this is due to I'm locally solving small pieces of steady states. So in fact, the numerical method is able to take this branch, automatically detect and put this exact branch, and here evolve, subtract the steady state, and then evolve the fluctuation. Now the fluctuation is passing through this discontinuity, put it away, and then I recover the steady state, because this steady state is stable. Okay? If not, another things appear. Okay? And this is due that my method is well balanced. Okay? It's high order, of course. This is first order, second order. In the third order, you are able to capture better the structure of the propagation of the shock due to the small fluctuation. A more real problem. So this is, a non-hydrostatic or dispersive shallow water system. So it's quite close to Serre-Grignard system. So here you have, H is the water depth, U the cell average of the average of the horizontal velocity. Here G is the acceleration of gravity. This is the bathymetry, so this is pressure terms, and then you have the correction of the non-hydrostatic effects. Then you have vertical velocities, average vertical velocity, and then this is the incompressibility condition written in this framework. Okay, so you have an hyperbolic system with a constraint that somehow is elliptic. It's like in the incompressible Euler system. And I want to simulate the propagation of a soliton propagating in a channel. This soliton is going to change the form because you have a slope, and then it's going to break and create inundation. Okay, in red is the laboratory experiment. In blue is what you obtain with a standard shallow water system that is not dispersive. So you cannot approximate, the propagation of a soliton properly. So it's what you observe. You have an error in the propagation of the wave. Okay, the inundation is not too bad. This is the reason why, shallow water models are very popular among the people that do simulation in tsunami modeling. Because even if the propagation of the tsunami waves are not well captured, the inundation are not so bad. Okay, this is a toy problem, but I could show you, Tohoku tsunami, and then you will see that a standard, very simple hydrostatic model gives you a very precise representation of the inundation. But of course, the arrival time is completely wrong, okay, and the propagation of the waves are completely wrong. And this is what you obtain with that model. So you are able to propagate the wave, breaks, and inundate. You must be careful in this framework because, okay, this system, the previous one, had also an energy associated. So you need to prescribe a proper numerical method that is able to control the energy, introduce the braking mechanism in order to break the wave. So it's a hard numerical problem to deal with numerical methods that are able to prescribe this. Okay, a more challenging problem. So you have a pool, it's time, okay?
Yes.
So, okay, you need to increase the complexity of the model, and we are able to do it. So, for example, here in this problem, what you have is a pool, you have buildings, and then you have a wave, and then the wave is going to enter into the city, breaks, and then we are able to compare with the measures, and things are not so bad. You could combine with more sophisticated model like landslide. So you have a landslide, and then you have a moving wave, and then you compare with laboratory experiments, and you match pretty well. And then you apply in real problems. So this is, for example, a project that we have with people in Italy. We are able to control, the tsunami generation by, this is the Stromboli Island, okay? And this is a volcano island, and then you have landslide associated to eruptions. And then we have collaborated with those guys in order to produce inundation maps. And they are quite precise with respect to measurements. So let's say this framework that, I'm finishing, okay? This framework, I only present you in 1D. I try to give, the main theoretical details about the construction of the numerical method, but of course then you need to extend properly to multi-D systems. New challenging problems appear, like, for example, this kind of problems. You need to do high-performance computing and things like that. So, okay, thank you so much for that.
Thank you, Manuel, for a very nice talk. Then we'll have some time for some further questions. If someone wants to ask something.
Just a curiosity, how did you start this collaboration with the Tsunami Center? Like, how was the first contact?
By chance, always by chance. So let's say we have, people in, we are from Málaga. So, okay, the typical problem that we could deal and we start is playing with floods. So you have strong rains and then we have floods. And we go, presenting this, not in a mathematical community, but, in other kind of congresses, like, this AGU Congress and EGU, so Congress related with the European Geophysical Union. So we were presenting, things about floods. And there was a guy sitting in the room. This guy works on the tsunami early warning system in Italy, and also in the Noah Center with the USA. Then, at the end of the talk, here I say, okay, I'm not interested at all in floods, but you are able to do the same thing with the tsunami waves. I said, well, I don't know. Give me, let's start to look about what are the kind of model that you want. And we start our collaboration by chance. So and then we start the collaboration with people in NOAA, in the USA, in Italy, and then we have a lot of collaboration with, people in early warning systems. So this is the combination. No. I remember my first meeting with those guys. I tried to show you, okay, I have a theorem proving positivity of water height, whatever. I said, who cares? Okay, you are able to do, but then, I tried to convince them we are able to do it, but then, mathematical aspects of, properties of the numerical methods are relevant. Because, for example, you want to capture properly the inundation, you need to ensure positivity of pressure, that is water height or density. So if your numerical method is able to preserve this, then okay, if you have a mathematical framework setting this gives you a very robust numerical method. And if you want to do uncertainty quantification, so you are going to play with, Monte Carlo things or whatever, you need to have a very robust method. So at the end, we start by chance, then I try to convince them that the mathematics are useful in that framework, and then we have a strong collaboration with those guys.
So we're in a little bit of a schedule.
Sorry.
No. I'm saying that we will not have time for any further questions because.
Quería solamente hacer un comentario histórico. ¿Puedo? Okay. Continuando con lo que él ha dicho, hay una cosa histórica que es interesante. el primer congreso de matemática aplicada que hubo en España, que se llamaba CEDIA, se celebró en 1978. Y la parte numérica estaba basada en colaboración con Francia debido a los contactos de una persona que fue presidente de SEMA, Valle, y fructificó en España, en Santiago y en Málaga. Se hacen muchas matemáticas de tipo marino. Ese es un trabajo que ha costado muchos años sacar adelante, como habéis visto, y que hemos visto crecer. Se trata de, por lo tanto, desde el año 78 hasta ahora, de una labor continua de trabajar en grupo, con grupos internacionales, ¿no?
Sí.
Es decir, Málaga y Santiago son, en el sentido numérico marino, el orgullo de las matemáticas que hemos visto crecer en España. Estoy muy contento de estar aquí. Gracias.
Gracias, gracias.
So as I was saying, due to some problems with the trains, which are not only in the accident one, but apparently there is another problem close to Málaga, we have to finish this a little bit earlier because now in Spain you have to fly instead of taking the train, and Barajas is not as friendly as Atocha. So I want to thank Manuel again for his very nice talk, and I would have liked to hear the remainder of the details, but I'm sure the details for that are really technical.
Some of them are technical,
Yeah.
and I don't have too much time to explain all of them.
So thank you again for coming.
Okay. Thank you.